Okay, so it's now my pleasure to introduce Rupert Verco, the Managing Director of Cobra Resources, and Rupert will be speaking on the economic in situ recovery of ionic rare earths. Please welcome Rupert.
Thank you, Peter, and thank you to the SAEMC committee for inviting me back. Next year, if I do get the invitation, please remind me to bring sunglasses and sunscreen. Must be the terbium in these lights. Look, Cobra, we've taken a very unorthodox approach to a rare earth discovery at our Boland project. And whilst we're not yet at a feasibility stage, we've taken a very considered approach in defining what our economic opportunity may be. And as we're working through our exploration program, we're growing in confidence that we can potentially place this project at the bottom quartile of the cost of rare earth producers globally. So since the peak of rare earth prices in 2021, there was obviously a lot of exploration interest in rare earths. And what we found in that time is rare earth occurrences in saprolite and regolith are not rare, but what is rare is the mineralogy that promotes or enables economic extraction is as rare as hen's teeth. And that's why we think our Boland discovery is different, and hopefully with a bit of technical supporting information I can convince you too. So our approach has been slightly unorthodox. Since we made a discovery that we spoke to you about last year, we haven't gone out and defined a resource. We've taken a different approach. We've focused on metallurgy, processing and hydrology. And why? Well, that's where the biggest investment risk sits with rare earths. And we want to demonstrate to our investors that we can address those risks before going out and defining a significant resource. Now, why do we see an opportunity? Well, it's obviously very commonly known that China dominates the supply chain in rare earths as it does with a number of other critical minerals. Why can they control so much value add in that supply chain to realise what's relatively a small industry in rare earths at the mining stage, valued at $7 billion, but capture up to $3.5 trillion in value add down that downstream supply chain? Why it is it's because that is underpinned by their low-cost mining in southern China that produces a significant amount of the world's heavy rare earths. And they're doing that through a form of in situ recovery. But that form of in situ recovery requires gravity, and clays aren't that permeable. So they struggle on, whilst they get the benefits of low cost and low capex, there's environmental risk, there's poor recovery, and there's lots of social issues, as we're seeing in Myanmar at the moment. Why Boland is different is we benefit from that ISR process. We're doing it in a jurisdiction whose geology has been proven in the uranium industry to enable a very cost-effective and low capex form of mining, and we can demonstrate to our stakeholders that we can do this mining under a very good regulatory framework with very low environmental and social risk. So where are we? We're not in that microscope. That's where South Australia's operating ISR mines are, but we're in the middle of the Eyre Peninsula on the Narrabee Paleo Channel. Earlier this year, we executed a sonic drill program, and we've subsequently installed a well field where we're currently doing our baseline hydrology studies and plan to, in the coming year, to execute infield tracer permeability studies. Since making this discovery, we've been working through the archives and looking at core in the core library, and we've expanded our position across the Narrabee and Yinini paleo systems. And what we're looking for is a unique occurrence of rare earths that isn't in saprolite, Rather, it's in the Patinga Formation and the Paleochannel sediments. This is our well field. When we first drilled this through air core, we defined 3 zones of low-grade mineralisation. With our technical understanding, and when we applied sonic drilling, we were able to understand the chemistry drivers that enable rare earths to be precipitated out in unique chemical conditions, and we've demonstrated that those rare earths are actually concentrated in high-grade zones, particularly zone 3, within permeable sands. Sorry, I'm technically hopeless. So, what have we done from a low-cost standpoint is we've, like many other companies, gone back through the state core library and reanalysed a lot of old uranium-focused drill samples, and we've been able to determine, based on pretty broad composites, that we've got rare earth occurrences over very broad areas of very anoxic zones in the paleo system. So this is giving us confidence that when we go out and focus on our attention on resource definition, that we have a significant target to go and define. So this is how our geology looks. We have 3 zones of mineralisation interbedded with very permeable sands, and zone 3, particularly the Patinga Formation, that forms a very unique chemistry boundary between acidic underlying saprolite and the reduced but alkaline environment within the paleo system in this location. Now, what's unique and different about our ore body as opposed to the traditional saprolite is 70% of our ore body is sand. Our rare earths, I can see my slide hasn't projected that well there, but our rare earths are absorbed to smectite and organics within that lattice of that sand, and what that enables is permeability. And here we have Rob Blythman, our exploration manager. He doesn't just get excited about porphyry systems. Regolith gets him very excited as well. And what that's enabled is us to test the permeability potential for us to apply in situ recovery as a preferred mining method. And with ANSTO, what we've demonstrated is we've demonstrated very high recoveries of ionic rare earths at relatively benign pHs. So what we have on the graph on the left here is the starting pH where we started our test is about 7, and over a period of time we've gradually reduced using the permeability of that sample that acidity down to about a pH of 5, where the rare earths start to liberate out of the system, and they continue to be desorbed until we take it down to a pH of 3. Total recoveries in this test from a sample nearly at 0.45%, were about 56% rare earths, 50% heavy rare earths. We've since done further metallurgy work. Where we've looked at how we can optimise the process. What can we do to our lixiviant to get higher recoveries without compromising the key economic factors for rare earths, which is 1, impurities, and 2, acid consumption. Currently, from that test work, our acid consumption sits under 15 kilograms per tonne sulfuric acid, and even at a pH of 2, we're at about 16, 17 kilograms per tonne. So the increase for the additional recoveries is negligible, and we're still recovering over 10 times more rare earths than we are impurities. Subsequently, we've just completed a second permeability study, and we've done that on an upper section of Zone 3 core, and what that has shown is we've smashed our permeability targets, and we've learnt from our initial tests that we may have compromised that first test with a little bit of saprolite. In this second test, we've achieved permeabilities of 121 metres per day, and subsequently finished what was first a 150-day test in 24 hours. And this has given us great confidence to now go out and drill a resource. And what's the benefit? What's the economic benefit of ISR, and why would we focus on this? Well, taking a leaf out of the uranium industry, which has taught us that the capital intensity of in situ recovery mining is a factor of, well, it's 10 to 15% of a conventional hard rock mine, and we believe it applies here. We don't need IX columns to process this. We're looking at a very simple titration process to be able to precipitate and remove impurities from our rare earths, and we're looking at membrane desorption to further purify our sample. And we'd like to think that we can demonstrate through further testing and the publication of a scoping study late next year, a CapEx bill under 100 million US. Now, this is where we've taken a very unconventional approach in our exploration. 12 months ago, as a team, we sat down and we said, what do we need to make this project a success? What are the cost factors that mean that warrants further investment, but also means that we're hitting the milestones that we need to? What's the level of acid consumption that's a barrier? What's the cost of wellfield configuration based on permeability? How much CapEx is going to be required for that? And as we've worked through this exploration program and focusing on metallurgy and permeability, we've been working to demonstrate and form these cost factors to further inform our work program going forwards. And we're not reinventing the wheel. We're applying a proven method of mining to a new form of mineralisation. I like to call them ionic mineralised sands. But what we can learn from the uranium industry through 30 years of development of ISR is ISR dominates the bottom quartile of production costs in global uranium mining and accounts for almost 60% of global production. If we look at the rare earth global cost curve and look at the Chinese production as opposed to the rest of the world, it tells a pretty stark picture. To be competitive, you need to be competitive with the producers out of China. And we believe through ISR we can get to that point. So what's next for Cobra? We've just been very supported by our shareholders and raised a nice amount of capital to really ramp up exploration in 2025. We plan to be out resource drilling later next month, or this month, and start to really firm up principles that need to be demonstrated to support a scoping study. So next year we're looking to scale up and take our permeability studies into the field through tracer tests, and hopefully use that infrastructure that's installed in the field further down to the track for a pilot study. So whilst we've ticked milestones, we've got more to go, and the next important one is obviously the definition of a scalable resource. So we're really excited about what we are progressing and what we're defining. It's taken a lot of very considered geological understanding of what consumes acid, what drives the precipitation of rare earths, and I encourage anyone who is going to look at rare earths through the next boom and bust cycle to really consider the chemistry advice to understand how active and what drives these systems. Anyway, thank you, Peter.